Hey there. Today we're going to talk about probability. Some of this will feel like review, but there will be some new things in it as well. We're going to start off and talk about the difference between theoretical versus empirical probability. And theoretical is what's supposed to happen given many trials. Empirical is more something like what happens from an experiment. Then we're going to dig into some more compound events, more complicated probability problems. We will end up using our counting principles today also. Now, this is a little bit tricky to try to do because we did something with our graphing calculator. You can actually do like some dice rolling. You can spin a spinner. You can do some different things on your graphing calculator in your apps. If you go to probability simulation in your calculator, it'll actually let you like roll the dice 100 times and how many sixes do you get kind of thing. We're going to skip over that here because I can't really do that through a video. Okay, this might be something a little bit more like empirical probability. Instead of us actually getting the data, we're going to be given a chart full of data. So here we have a situation that the safety and security department at a college ask a sample of students the following question: do you think the college has adequate lighting on campus at night? And this is kind of just the tally of all the responses they got. So looking at this, it says, what is the probability that the student committed to a yes or no response? Okay, so yeses are right here. 120 people said yes, 109 said no, but see, 28 of them had no opinion. And so our total number of students asked actually is this bottom corner right here. That's the sum of those. It's the sum this direction. There were 265 students asked. So the probability that they committed to a yes or no would be all of these people. So what is that? 237. So when you're doing probability, it's the number of successful responses. So that'd be the 237. Over the total, which is 265. And you can leave that as a fraction or go to a decimal. You'll just have to pay close attention to your directions today. All right, what is the probability that a student is male or had no opinion? Okay, so male would be right here, a total of 103, or had no opinion, that's a 28. So we would add those two together. The problem with adding the 28 to the 103 is that you double counted these guys right here. The males that had no opinion, those 4 people got counted this direction and this direction. So instead of taking I still could do 103 plus 28, but then subtract 4 from that because this 4 got counted twice. So then that would be a total of 127 out of 100 or 265 students. Okay, last one. What's the probability that a student said yes, given that you asked a female? All right, so this is kind of a new notation for us. This is the probability they said yes, and this bar indicates that this has already been dictated, that we were only asking females. So what's the probability that they said yes, given that we ask females? Well, what this does right here is it reduces the total possible. We're no longer looking at the 265. We're saying, okay, of the female, we're specifically looking at female responses only. How many said yes? So I'm looking at the females this way. So there were 162 females. So that's going to be my total. That's what's going to go on the bottom. The top is how many of those said yes. So of those 162, 36 said yes, there's adequate lighting. Now, those are both even numbers. That would reduce. We'd always want to try to reduce that. Let's see, that's an 81 and an 18. Oh, you know what? That keeps going. 9 goes into both of those, so 2/9. That would reduce to 2/9 right there. Okay, so theoretical probability is what should happen if you do some sort of survey and ask enough people or roll the dice enough times that it should average out to here's theoretically what's supposed to happen. Okay, just some notation. This is the probability of some event occurring. And when we're doing probability, like I said earlier, it's always the number of successes over the total possible. Now, remember that the sum of all the possible outcomes should equal 1. So the fact that the sum should equal 1 leads us into this idea of complements. So the probability that an event does not occur is the complement. And our notation is this little hash mark right here. So this is the probability that some event does not occur. That's just going to be 1 minus the probability that it did occur. It's almost like this. If I am let's say a 70% well, I'm better than that. I'm an 80% free throw shooter. Okay, so if I'm an 80% free throw shooter, then the probability that I make a shot would equal 0.8. So does it make sense then the probability that I miss it would be a 20% or a 0.2? And all that is 1 minus 0.8. That's the probability that I miss it. That's the complement, making it, missing it. Those are complements, they're opposite scenarios. One of the places that we talk a lot about probability is with dice rolling. It's kind of a gambling thing, and that's one of the places that probability is used quite a lot. And so it is important to understand what are all the possible outcomes. How could this play out? If you're rolling 2 dice, this is a nice little chart that shows how this might play out if you roll 2 dice. Now, this means, and you kind of, when you're rolling 2 dice, you have to think of them as being like, they're 2 different colors, they're 2 distinct things. So rolling a 1 on one of them and a 2 on the other is different than vice versa. So you can see that rolling a 1 and then a 2 is considered a different outcome than a 2 and a 1. Now, the sum of them is still 3, so that holds, but maybe you're looking at what's happening with the dice individually. That's why we look at that as 2 separate outcomes. Now, looking at this, there are some patterns within this. If you look at the sum of, let's say, getting a 7, well, that would be this right here, a 1 and a 6, 2 and a 5, 3 and 4, or 4, 3, 5, 2, 6, 1. And all of these, when you're looking at the sum of the dice, always fall on a diagonal. So right here on this diagonal, that's a 1, 3, 2 and 2, 3 and 1. Those are all the 4s. So that kind of helps you. So what's the probability that you get a sum of 8? Okay, here's my 8 diagonal, and that's 5 different ones. Now, that's the number of successes. The total would be 36 because there's 36 different outcomes listed there. Okay, what's the probability you don't roll a sum of 8? Well, that's just the complement, so 1 minus 5 over 36. And think of your 1 as a 36 over 36. So then that would end up being 31 over 36 is the probability I don't roll a sum of 8. What's the probability you roll a number greater than 9? Okay, well, greater than 9, you start looking at, well, that could be it's not or equal to 9, so it wouldn't count the 9, but it would count the 10s. So here are the 10s, or the 11s, or the 12. So there's 6 different successes there out of a total of 36. That, of course, reduces to 1/6. Be able to create this chart or envision it at least some way, because we do a lot with this dice rolling. Okay, let's move on to a different thing. As promised, I said we'd use some of our counting principles. So let's say you have a committee of 5 people. They're going to be formed from a group of 8 men and 6 women. Find the probability that the committee will consist of 3 men and 2 women. So to do this, you're going to have successes over total still, because we're doing probability. So a success is actually having this happen. The total is the fact that you're just creating the committee. So I'm going to start with, I guess, the denominator on this. So the denominator is just, hey, I've got these people, I'm going to make a committee. So how many people are there? 14. And how many people are going to be on the committee? 5. So that's the total number of ways that I might create the committee. But the success is having just the right number of men and women. So that's actually a 2-part thing. I'm going to start off, let's do the men. There are 8 men, and I want to end up with 3 of them on the committee. So this would be all the different ways that that could play out. And so I'm going to multiply here by another scenario of the women. So I want to make sure that I get exactly 3 men. So that means I need exactly 2 women. So I'll have 6 women, and I need 2 of them to be chosen. When we type that in our calculator and divide it out, I get a probability of 0.420. We usually go 3 decimal places on probability. Okay, let's try another one like that, since those are kind of harder ones. Because your class is given a list of 20 study problems, from which 8 are going to be part of an upcoming exam. Now, you only know how to solve 15 of the problems, so find the probability that you'll be able to solve 6 of the 8 on the test. All right, so do you know enough of them? If you got 15 out of the 20 that you know how to do, is that enough to still do well? Let's find out. If you're setting this up, it's kind of like before. Your total goes on the bottom. And the total is that there are 20 questions, and we're just creating a test. 20 questions, I'm going to create a test. 8 are going to be on that test. All right, so that's the total number of ways I can create it. Now, I've got to come up with a scenario of I can do some of them, and some of them I can't do. So let's start with the ones I do know. I know how to do 15 of those. How many of those do we want to end up with on the test? 6. But then I don't want to get ambitious here. I want exactly 6. I want that to happen. So now I have to also account for how many ways then could the 2 that I don't know how to do, how could that play out? Well, that means if I knew how to do 15 of them, then that means 5 of them I don't know how to do. And of those 5, 2 are landed on the test. Okay, so now we type that in our calculator. And just doing that, I'm assuming, I'm going to assume you know how to do your combinations, that you've done that lesson. All right, I'm kind of pausing the video and typing in the answers into my calculator. So I ended up with a 397 probability that I'm going to get 6 of the 8 correct. Okay, how about this? What's the probability that I could ace it? Well, let's set it up. Actually, I'm going to let you try to set this up. So with this same mentality right here, could you set up this scenario? So pause the video and try this one on your own. Okay, this was my setup. The total number of ways the test can get created is still this. I break it down with the 15 I know how to do and having all 8 of them land on the test. The 5 that I don't know how to do, not having any of those on the test. Now, I remember from the other day that this is just equal to 1. So ultimately, I just typed this divided by this in my calculator. I got 0.051. So not very likely that I'm going to be able to ace the test if I only know how to do 15 of those problems. All right, I know you're too young to gamble, so let me talk a little bit about the Powerball. Okay, so the Powerball is a lottery in which you have to pick 5 white balls and 1 red Powerball. The white, I think of them like ping pong balls because it's like this big bingo vat thing with these ping pong balls bouncing around in there, and they spit out the numbers. Well, the white ping pong balls are numbered 1 to 69. And the red Powerball is numbered 1 through 26. So they have all of these little ping pong balls in, and then they shoot them out and say, oh, here's the first white ball, and here's the second white ball, and here's the third, and here's the fourth, and here's the fifth. Okay, now, because of that, it's worth noting that order is not important in which they come out. And they also cannot repeat. Once the ball is out of there, then that's the only one. But I don't care. I said this is the first, this is the second, this is the third. It doesn't really matter. You just have to have the 5 numbers. And they don't have to be in the order that they spit out of this big tumbling ball. So, because of that, I'm doing combinations. We're going to set this up similarly to how we did the other problems. You're going to start off combinations of, okay, how many different ways can this play out? Okay, now I said this is like the last one, but it actually is a little bit different because I am restricted on how the Powerball numbers get chosen. I have 69 white little ping pong balls, and I am spitting out 5 of them. It's not like I'm going to do 6 white ones this time. Nope, it's always 5 white ones, and then you have 26 red ones, and you're going to choose one of those to be the Powerball number. So that's the number of ways that it can happen. Now, this isn't really the tricky part, is how many successes are there? How many successful sets of winning numbers are there? And the answer to that is there is only one. You just have to have all the right numbers. So there's only one successful Powerball ticket. Now, it is possible, and it certainly does happen, that 2 people randomly happen to pick the exact same numbers. And if that happens, then there's 2 winners. But it's not because there were 2 winning sets of numbers. There's one set of numbers that works. Okay, if I type this in my calculator, you're going to see why you should not be buying lottery tickets. So it's a 69 choose 5. And then I'm going to take that times. I'm not even going to type this in my calculator. I know 26 choose 1 is 26. So I just take it times 26. Okay, so this is a 1 in 292201338. Okay, so let's look at what that is. A 292 million chance of you winning the Powerball. So not very likely. The next thing I want to talk about is compound events. Okay, so these are going to be a little bit simpler probably than that we're not going to deal as much with the combinations. This is more basic probability, but to say I have compound events, that means there's multiple things going on and I have to figure out what the deal is. So if you want the probability of this or that happening, something like that, where you see it like this, the probability of A or B occurring, well, anytime you see the word or, that means you should add the probability of A plus the probability of B. But what you have to remember is whether or not they are mutually exclusive. That is a nice probability, mathy kind of phrase, mutually exclusive. If they are mutually exclusive, they are totally different. They have nothing to do with each other. They will never occur at the same time. So let me show you some examples. Let's say you randomly draw one card from a deck. What is the probability that it is an ace or a king? Well, the or tells me I'm going to add. So the probability that it is an ace is 4 out of 52 cards. There's 4 aces in the deck out of 52. Or means I want to add. Now I want it to be maybe be a king. Okay, well, there's still 4 kings in the deck over 52 cards. Add these together. Well, actually, maybe you reduce them first. I don't know. That reduces to 1/13 plus 1/13. Add those together, and we're going to get 2/13. So that's the probability that you get an ace or a king when you draw. Okay, let's try it again. What's the probability you get an ace or a heart? Okay, it feels like it's the same thing. But what's different here is that aces and kings are mutually exclusive. They are totally different from one another. But an ace or a heart, those are not mutually exclusive because you could have the ace of hearts. And so you're getting the ace and the heart at the same time. So what that means is I can do the 4 over 52, the 4 aces, and then the hearts, it's all split up. There's 52 cards total divided by hearts, clubs, spades, and diamonds. So there's 4 suits. If you divide 52 by 4, you get 13. So there are 13 hearts out of 52 cards. And I could add this up. The problem, though, is that they are not mutually exclusive. And the ace of hearts got counted right here, and it got counted right here. So I have to subtract any overlap that there is between those two things. And in this case, it's just the one card, the ace of hearts, that got counted twice. So I have to subtract that out. So that ends up being 16 out of 52, which does reduce because 4 goes into it 13 times. All right, so that's how you work through or situations. Let's take a look at and situations. The probability that this and that happen. So when you see the word and, you should be thinking multiplication. You're going to multiply the probabilities. Now here's a little notation. This bar, remember what that meant earlier? So what's the probability of B occurring given that A already occurred? That's what that bar means. Okay. Let's try some. It says randomly draw 2 cards from a deck. The probability that I get an ace, and then I draw another ace. So how many aces? 4. Out of how many cards? 52. And tells me to multiply. Now, when I do this, though, I am assuming that that ace is already, the first ace I got, I'm leaving that out. Sometimes they use that phrase with replacement. If I drew the ace and then I put it back into the deck, then I'm opening myself up to redraw that ace. So there's more aces in the deck. But that is not typical. It's usually once you've drawn it, it stays out. So that's the whole find B given that A already occurred. So given that I already found the first ace, what's the probability the next card will be an ace? And that's only 3 out of, be careful, not 52, it is 51. Okay, you can do a little bit of reducing, or you could multiply straight across. I guess I'm just gonna, I'm gonna reduce. So the 4 50-seconds actually reduces to 1/13. And the 3 over 51 reduces to a 1/17. And I don't know what 13 times 17 is. All right, so I'm going to have a 1 out of 221 chance of pulling an ace followed by another ace. Okay, next one. This is my screens got cut off a little bit. So this is the probability that you get a pair. So it might be a pair of 2s, it might be a pair of aces, might be a pair of jacks. Who knows? All right, so what's the probability that the first card you pick is the correct card? Well, really, that is 52 out of 52, which is really just going to be a 1. So because I don't care what the first card is when I draw it. But once I've designated what my pair is supposed to be in from that first draw, now I do care. So let's pretend I pulled an 8. Okay, great. So I'm trying to get a pair of 8s. I already got the first 8. So how many successes are still sitting in the pile? Since there's 4 total of them, and I already drew one of them out, there's only 3 successes left in the deck. And there's only 51 cards left in the deck. Okay, so then we can, actually, I know 3 over 51 reduces to that 1/17th, and 52 over 52 is just 1, so that reduces to a 1/17th probability. Oh, looky, another gambling game. Okay, so this game is called roulette, And it is the one where they spin the ball around and you're putting your chips on these different numbers, hoping that the ball will land on your number. Okay, so if you look at this, there are 36 numbers. Some are red, some are black. It's supposed to be, I'm not sure this picture is accurate. I know it can be different. I know that usually, okay, so then up here, you have a 0 on the board. You can see that it's right here is the 0, but usually there's also a double 0. So there's 2 different greens there. The whole point of that is so that when you go in there and you put your money on black, well, it's not really a 50-50 chance because it could be red, but it could be green. And those greens are actually where the casino makes their money. Just it hits green often enough that they come out ahead in the long run. Casinos are not built on a bunch of us out there winning money. They are built on the casino winning money. So we get lucky once in a while. Let's look at this now. So the probability of a 36. So if you look at this, what is the probability? It's not so much the board because I have all these extra side bets I can do. It's really about spinning the wheel. So what's the probability that it gets to be a 36? Well, how many 36s are on there? Just one. Out of how many numbers are on there? Well, there's the 36, but there's also the zeros. So it's a 1 in 37 chance that it lands on a 36. Okay, what's the probability it hits black? Okay, so without counting them all up, it's supposed to be even. There should be 18 blacks, 18 reds, and then some greens. Okay, so how many blacks are there? Well, there's 18 of them. Out of how many total? 37. What's the probability it's not black? Okay, well, that means it's red or maybe the green. And so that actually is a 19 out of 37. All right, how about the probability that the dealer spins it and it ends up green, and then he spins it the second time and it ends up green again? Okay, well, green is 1 out of 37. And to get, oops, I don't know what that is, 1 out of 37. And then another green would be, now these are independent of one another. What happens on the first spin has nothing to do with the next spin. So it's still a 1 out of 37. So whatever 37 times 37 is. So I end up with a 1 over 1,369 chance that it goes green and then green again. All right, how about the probability that it is a red or an even? Okay, so remember, and was telling me to multiply, but or tells me to add. The probability that it is red, well, there were 18 of those. I feel like I remember we counted these once and they didn't really come out like that, but I'm pretending that is the way it is because it should be that way. So this was just a Google image I found. So 18 reds out of a total of 37, or tells me to add, how many even numbers are there? Well, there's going to be an equal number of evens and odds of the 1 through 36. So that'd be 18. But 0 is actually considered even, except in gambling. Okay. I mean, 0 is considered an even number, but if you look at this list right here, if you look at the gamble thing right here, an even, they don't really, if you decide to bet on evens, they don't count 0 as an even. I don't think. I've played roulette, but I don't know. I don't get that deep into it. So let's not think about the gambling rules, and I wouldn't expect you on a test to know all the gambling rules. Let's just say that for evens, it would be the 18 of them of the 1 through 36, but 19 with the 0 in there. Okay, so not to dig into the weeds there of all the details of gambling, but I would normally add these, but there's something else I got to think about. How about the evens that are red? Didn't I count them right here and here? All the even red numbers? Okay, well, that's problematic. If I double count it, then I have to subtract out everything that gets over counted. Okay, because red and even, that's not mutually exclusive. That could happen at the same time. And maybe this is where we count. Don't count. Don't go look at the picture. It's just all like what it should be for the probabilities to play out evenly all the time. So if there are 18 reds, half of them are even, half of them are odd. So I'm going to have to subtract out of those 18, I'm going to have to subtract out 9 of them that got overcounted. All right, so add that across. That ends up being a 28 out of 37 probability. All right, last thing. There's so many different things that we have covered today. Keep your notes out when you're doing your homework. Lots of different types of problems. And I'm going to tell you, this is the hardest part of the test. It feels like the sequences and series was tough. It's really the probability, because you really have to have a full understanding of how to set each one of these scenarios up. All right, last thing is sequential events. What is the probability that a couple has 4 kids and they all end up being boys? Well, this is a nice little picture of me and my family, because my husband and I have 4 kids and we ended up with 4 boys, which was awesome. Love it. So let's think about that. It feels like, oh, that's so weird. Why would to end up with 4 boys? Well, it's actually, well, I guess let's look at what the probability of it is. What's the probability that the first kid was a boy? Well, it's a 1/2. And the next kid, so that means multiply. Well, you're really starting over. And the next kid would be another 1/2. And the next kid, and the next kid. All right. So it's a 1 in 16 chance that you have 4 kids and they're all boys. Okay. That seems weird. The same probability would happen if it was all girls. What makes it seem weird is that if you, let's say you had, what's the probability you had 2 boys and 2 girls? The reason that that is more likely is because it could go girl, girl, boy, boy, or you could do girl, boy, or boy, boy, girl, girl. There's all these different ways for that to play out. And that's why it ends up being more likely to have some of each. Okay, let's look at the next scenario. Suppose Mike Trout has a batting average of 305. What is the probability that he gets a hit all 4 times he's up to bat in the next game? All right. So what's the probability he gets a hit the first time? It's a 0.305. Now he gets up to bat again. What's the probability he gets another hit? Well, this is his batting average. So that's the probability. Now, I am assuming, I don't know if this is true or not, that they don't adjust his batting average based on what he did last inning, kind of thing. Let's say for the whole game, we're going to stand by this. But man, if he gets 4 hits in a row, his batting average is going to go up. But every single time, it's this 0.305. 0.305. And I would just type in my calculator then, 0.305 to the 4th power. And so the likelihood that he gets 4 hits, pretty slim, 0.00. And if I'm going 3 decimal places, that would round to a 9. Okay, lots of stuff there. Hope you understood it all. Good luck with your homework. Bye.